Today I'm going to be presenting on meteorology and air quality modeling using the AWS Parallel Cluster Cloud Service. I'd like to thank my co-author and colleague at LADCO, Dr. Singal Nirgui. In May and June 2017, LADCO participated in a field study called the Lake Michigan Ozone Study to investigate the physical and chemical drivers of ozone pollution along the shores of Lake Michigan. One of the key findings of that study was that to model the dynamics of the lake breeze, which can be an important factor during high ozone episodes in the region, regional climate models like WRF should be run at grid resolutions finer than 4 kilometers. LADCO is in the process of updating our air quality modeling platform at the time to a new base year, and we designed a WRF configuration to support that base year that included a national 12-kilometer resolution modeling domain, a large 4-kilometer domain that covered the entire Great Lakes Basin, and two 1.3-kilometer domains, one that covered the entirety of Lake Michigan, and the other one that covered the eastern part of our region from Detroit down through the Ohio River Valley. The problem that we faced with this new modeling configuration was that our local compute cluster, which had upwards of 300 CPUs, was not sufficiently networked to support distributed parallelization. We could run jobs on each machine, but not across machines, and ultimately the WRF runs that we designed would not be possible on our local cluster. There just wasn't enough computation power available. So to address this barrier, we developed the capability to run WRF on a cloud service. Conceptually, we recognize the need to expand our modeling capabilities to the cloud for various reasons. Access to flexible high-performance computing was just one reason. We didn't need to run jobs that were too large for our local cluster all the time, but we did need to have flexibility to scale up when we did need a solution. There was also a demand from our state members to have access to flexible and scalable Linux computing capabilities. Some of the state IT programs were generally not well equipped to administer high performance Linux systems. And the Fortran-based modeling software is not easily built by system admins who are used to using Linux package managers like Yum. So we also saw opportunities for easier transfer of modeling capabilities and modeling knowledge to our states through cloud-based modeling systems. So we had a few motivations for moving our modeling into the cloud. I had a vision for a modeling platform as a service since my days with the CMAS Center. I spent many years supporting community members at CMAS, struggling with compiling libraries and gathering data and porting the modeling software to new computing infrastructure. Some of the early work on modeling in the cloud that I did with the CMAS training program used the Amazon Web Services cloud or the AWS cloud to serve pre-configured training instances. And I demonstrated through this the potential of the cloud for distributing turnkey modeling solutions. At LADCO, I was able to further develop this concept to a scalable modeling system with a more complete suite of modeling and analysis software. And with larger data appliances or data drives that could be attached to software and application instances. I needed to figure out how to operationalize the system, move it beyond kind of small training machines and test systems, and also how to do it inexpensively. So at the outset, I hired a contractor, Ramble, to do some due diligence for me. They scoped out different cloud services and made some recommendations for how to best do modeling in the cloud. Ramble recommended that I take a close look at the Python-based system CFN cluster that was available for Amazon Web Services at the time. Ramble listed the merits of other cloud services besides AWS, namely Google Cloud and Microsoft Azure, but I was really intrigued by CFN cluster. And I had experience and familiarity with AWS from my past work at CMAS, so I chose to go with AWS. CFN cluster provided a way to configure and provision a Linux high-performance computing system from a command line, from a Linux command line. It created a central master node that ran continuously and then enabled the creation of on-demand compute nodes that only ran when you needed them. So with CFN cluster, I'd request a relatively small and inexpensive master node. And on that master node, I would develop, test, and issue run scripts. And then once I had my applications built, I would define and request larger, higher memory compute nodes that had the power to run big modeling jobs. The compute nodes are called using job scheduling directives. So with a scheduler, a system like SGE or Slurm, when you issue your run script, the job scheduler interfaces with the provisioning system, CFN cluster, for example, to call up the compute nodes. And then the compute nodes shut down when they're not being used, when they sit idle after a period of time. At the time of development, AWS was transitioning from CFN cluster to a similar system called Parallel Cluster. This was in about 2019 or so. And Parallel Cluster continues today and is in active development, and that's what we're using. Each new version of Parallel Cluster adds new and improved features. It's well supported, well documented. So the other challenge that I faced, now that I figured out how to access big computing resources through AWS, was to make it inexpensive. And so AWS has two different types of computing instances, on-demand and spot instances. On-demand instances or on-demand hardware, they have the highest priority and persistence, meaning that when you request the resources, you get them immediately and your jobs will run without interruption. Spot instances are up to 80% cheaper than on-demand, but you can face latency with instance provisioning, and you may experience job interruptions if you're in a high demand region with on-demand customers requesting the instances that you're using. So this basically means that, with spot instances, you can request the hardware and request the resources, but you're lower priority than the on-demand customers. So your jobs may wait in a queue and just not start. Or if they do get in a queue, if someone's willing to pay full price through their on-demand side, your jobs will get kicked out. So what I figured out is that if you're willing to use instances that are a generation or two old, so some of the older hardware available through AWS, you can actually find availability to provision and maintain spot instances. And there's a tool that AWS provides called the Spot Instance Advisor, and it shows you within different AWS regions the different instance types that are available, the savings that you get for that instance type over on demand, and then the frequency of interruption. And the sweet spot I found is that if you find instances that have a less than 5% frequency of interruption listed on the Spot Instance Advisor, these have really proven for us to be available and stable as spot instances, meaning you find an instance that's got a lower than 5% frequency of interruption in the list, your jobs pretty much get in immediately when you ask for those instances, and your jobs continue to run and don't get kicked out of the queue as often. So my design for our operational modeling platform as a system does not use containers. I tried using a Docker system at the beginning, but I couldn't figure out how to scale it to using MPI. I couldn't figure out how to get it to really parallelize across a large number of instances. I know this is possible, but I couldn't figure it out a couple of years ago. So I tried a different approach. Let me make a quick note on terminology. An instance is the AWS computing hardware. There are dozens of different instance types with various types of memory and numbers of CPUs and types of CPUs. And so when you build a compute cluster on AWS, you need to specify the instance type that you want to use. You also have to specify the operating system. In my case, I used Amazon Linux. And so you get a combination of your operating system on the hardware, the instance that you request. And then you also need to define your disks or your data volumes and the number and size of the disks that you want to attach to your compute cluster. So my alternative to a container-based compute cluster was to basically build a modeling system with interchangeable and reusable pieces. The central part of this in my design was an applications volume or an applications disk. It's basically a disk with all of my applications loaded and compiled on it. And the idea was once I built this applications disk, I would make copies of it or images and reuse those volumes across different compute clusters that I spun up. I build my applications on a relatively small volume of like 100 gigabytes or less, and I attach it to a fairly light instance because I don't need a lot of processors for just compiling. You need to make sure there's enough memory on the instance to compile programs. So I'll usually pick an instance that has at least 16 gigs of RAM or so. Then once I have my applications disk built, I save that volume to a disk image. Amazon calls it a snapshot. So then when I start up a new cluster, I attach a copy of the snapshot to the instance. And as long as I keep the same operating system, Amazon Linux in this case, that I use to compile the programs, I don't need to do any recompiling on this new cluster. All of the executables work. For example, I have a WRF compile that I first built back in 2019, and the executables still work on the instances that I'm spinning up and running today. So along with the applications volume, I also attach data volumes for input and output data. These can be either blank volumes onto which you move data once the cluster is running, or you can preload data onto a volume and save that as a snapshot. And then this would allow you to have kind of an input data volume that you attach to different compute clusters. And the input data volume would already have all the data preloaded onto it. So this schematic basically shows the design of our AWS modeling platform cluster, where I've got online data storage, disks attached to a master node. And then the master node calls up these ephemeral compute nodes through the P-cluster system that only gets spun up on demand. The central master node, it's relatively small. It doesn't have a lot of RAM and it doesn't have a lot of processors, and it costs about $2 a month to run continuously. To this instance, we attach, as I said, the applications volumes with all of our software and any number of data volumes. The system is really flexible and scalable. For example, if you configured your cluster to use 32 core compute instances, if you run a job that only requests 32 cores, then only one compute instance will start up. If you requested another job that needed 96 cores, then 3 instances would be started up. Once the jobs terminate, then the compute instances shut down and you're no longer charged for them. So here are some results from our experience at LADCO using AWS for both WRF and CMAS modeling. Each row in this table represents a different simulation. We've used 3 different instance types for our production runs here. C4 2x large are 4 dual core processors with 15 gigs of RAM. R5 2x large are memory optimized instances, also with 4 dual core processors, but they have 64 gigs of RAM. And then the R4 16x large instances are 32 dual core processors with 488 gigs of RAM. The variability in costs across these different runs are related to the complexity of the modeling job. So if you look at the 2 cheapest runs in the second and last rows of the table, these were pretty simple 12-kilometer continental US CMAS simulations. There were no nesting, no source apportionment tools used, and they ran for at about $2.80 per model day. The WRF runs on the top row were fairly complex. They had, as I mentioned, multiple grids and multiple 1.3 kilometer nests, and this cost about $8.33 per model day. The other CMAS runs were pretty big PM source apportionment jobs. They were on only a single 12-kilometer CONUS domain, but because there are so many PM species tracers in CMAS, that as you add tags, they begin to demand a lot of memory. And these CMAS PSAT runs range from $7 to $12 per model day. I should note that these numbers aren't exact. I wasn't tracking costs by simulation, but more by the instance type we were using, and then looking at the dates when those runs were operational. There was some overlap as some of the runs were running at the same time, and so distinguishing the costs were a little bit difficult, but I would say these are better than ballpark estimates, but not exact. So in general, you can see that we spent between $1,200 and $5,000 per CMAS simulation, again, depending on the complexity of the modeling configuration. These are compute costs only. The online data storage costs ranged from about $200 to $500 per run, and they used, about a 10 to a 14 terabyte disk space per simulation. This chart shows our daily AWS computing costs in 2020. The days are on the x-axis and the daily cost is on the y-axis. And these show when we're running our WRF and our first CMAS runs on AWS. The dark red lines are the compute instance, the daily compute instance costs, and the light red line is the S3 offline storage and data transfer costs. Our first WRF 2016 run was in February and March, and that period was run kind of in fits and starts because it was our first operational run on AWS. We didn't know how best to submit the job to the cluster. You can see that there's a lot of kind of spikiness in the run. The compute nodes were coming up and down, and as a result, the simulation dragged out for about 2 months. When we ran our second WRF simulation, which you can see that Illinois EPA 2016 WRF simulation down in August, we ran most of the 15.5-day chunks at once, meaning we submitted a bunch of jobs all at the same time. You can see the daily costs were more expensive because we were spinning more CPUs at any given time, but because the simulation completed in about 3 weeks as opposed to 2 months, it actually ended up being less expensive than the first simulation that we had run earlier in the year. The spikes in the S3 costs, these were the offline disks, they came in when we were downloading data from the cloud to our local computer. So S3, you incur costs for the data storage and also for egress fee. They're downloading the data from the storage appliances. You can upload data for free, but downloading costs money. We did a test in September, and you can see that big spike on the chart where we wanted to see whether S3 was an effective way to transfer large amounts of data. And we had about 5 terabytes of WRF output sitting out there that we wanted to send to Illinois EPA. And, after some trial and error of getting Illinois EPA, to get the AWS command line interface installed on their computers, and that took about a month, they were actually then able to download the entire 5 terabyte volume in about 24 hours. And it costs a little more than $500. So that really proved to me that S3 is really a great way to move large volumes of data electronically. I had never been able to move terabytes of data like that electronically, and the fact that we did it in under 24 hours, I think, was really remarkable. Couple notes on data management. I've talked a lot about computing on AWS. The data management is also a really important consideration for managing your costs. As I mentioned, really the art is to figure out how to keep your online data volumes small. These are the online disks. Keep them as small as possible because that's where costs can start to add up. Our workflow is to put model input data into S3, into what's called an S3 bucket. And then we've instrumented our modeling scripts to basically move data automatically. So to download the data files needed for each simulation day from S3 and then delete them when we don't need them anymore. There's a command line interface with AWS called the CLI. It's fully scriptable. So you can basically put file loading directives into your modeling run scripts. The scripts also post-process and move the output data off the online disks at the end of a simulation day. The S3 system is really easy to work with for tracking costs, and it's really an integral part of LADCO's long-term data storage plans. And also we're using it in our active modeling runs for staging and storing data. And as I mentioned, it's also a great solution for transferring data to your partners. These are our lessons learned. All of our modeling is done on AWS Spot instances. We're not doing any on-demand instance modeling. I figured out, again, that if we're willing to use a generation or 2 older instances, we can get stable and available computing at deep discounts, as much as 80% cheaper than the on-demand instances. And we have found that AWS is a completely viable solution for meteorology and air quality modeling. Its AWS Parallel Cluster is fully operational now at LADCO for our regulatory modeling runs. We've used it for ozone attainment demonstration modeling and regional haze progress demonstration modeling. And it allows us to run large and more complex simulations than we would have been able to do on our local compute hardware. Once our simulations are ready for production, we run as many CPUs as we can to turn the job around quickly. We were at first hesitant to use the larger, more expensive instances, but we later found that the speed that you pick up by using more CPUs allows the runs to complete more quickly and ends up costing about the same if you run longer on slower, smaller instances. So you get the runs done more quickly and faster at the same price. I should note that I spent about a year and $20,000 of computing time plus labor to prototype and figure out how to use AWS for WRF and CAMX modeling. So there was an investment to develop these capabilities, but it's really paying off now that we're operational with it. And there was a learning curve there, and I'd like to try to pass off some of this knowledge to the community. So I'll continue to figure out how to save costs. One thing that we're doing now is to shut down the clusters more frequently. The data volumes, the online data volumes, are provisioned and used and incur costs whether you're using the storage or not. In other words, you're paying for that 4 terabyte disk regardless of how heavily it's being used. It's not the same as the compute instances that they literally terminate and stop incurring costs when you're done with them. So one thing I've learned is not to let these compute clusters to sit idle. We run a job and then we shut down the entire cluster. You save the applications volume first, so you kind of have an image of the scripts and the executables that you use. You move all of the data off onto S3, but then you shut down that cluster as quickly as possible. Also working on managing our S3 storage costs. There's different tiers of storage on S3 depending on how often you access the data. The more accessible disks are more expensive, and we've been working on kind of pushing the data around to kind of the cheaper S3 storage solutions to manage those costs. I'd really like to work with others in our community who are using AWS or other cloud services for WRF, CAMX, and CMAC modeling. I need to see how others are managing costs and how they're using the system and optimizing their runs for speed and efficiency. Personally, I'd also really benefit from someone with more MPI experience than I have to figure out the best way to interface with the AWS hardware. Am I using Slurm, the job scheduler, correctly, and in the most efficient way to get the speed out of the jobs and the hardware? I just don't know. So stay tuned. Steve Fine from EPA and I will be forming a national work group to gather people interested in using the cloud for air quality modeling. I'm hoping that this work group will transfer knowledge and capabilities and tools around the community to get multiple people sharing information on best practices for air quality modeling in the cloud. Thanks for your time.